This is the X-47B autonomous aircraft. Now this thing is completely automated, software controls it, it lands itself on an aircraft carrier and stops. Now we're going to be looking at the testing, flight testing of this thing. So we've got flight testers, humans supervising this automation, but the automation is running and hopefully it works. So here's what's going on. The design intent of this thing is to have a fully autonomous aircraft to land on a carrier. And one of the examples of autonomy are these crosswind limits. So there are these crosswind limits where the aircraft, if your wind is blowing too strongly to the side of the runway, you can't land. It's going to blow you off the runway. So how does the aircraft deal with this? Well, the aircraft, now normally a pilot would talk to the ground station and figure out what the surface speeds are. Aircraft can't do that, can't get on the radio and talk to a human. So what it does is it calculates winds at altitude and uses that to estimate if the surface crosswinds are going to be too high or not. Now you might be guessing, well, wait a minute, the winds at altitude might be different than the surface crosswinds, and you'd be correct. But it is seen as an estimate. So it will do this calculation, and if the winds at altitude are too high, it will say, well, probably the surface winds are going to be too high. I'm going to automatically abort the landing, and it's going to wave itself off autonomously. It has no capability to receive actual surface wind from the tower. Now, that's how the autonomy works. What are the flight testers doing? Well, the flight testers are human beings. They can talk to the tower. So what they do, and by the way, it's normal to see a difference between winds at altitude, even at 1,000 feet, and then see a drastic reduction on landing. But what the flight testers do is they receive wind speed directly from the tower, the actual surface wind, and they can independently assess whether it's going to be a problem for the aircraft on landing. And they can anticipate if it should wave off or not as they're monitoring. And they do have the ability, if all else fails, they have the ability to override the automation and force a landing. There are maybe 10 criteria that can cause this thing to wave itself off. This is just one of them. And if for whatever reason you've got to get it on the ground, they can override that. Okay, that's the information I'm going to give you. Let's do STPA. So we've got step one, define purpose of the analysis. Well, let's prevent loss of life for sure. Let's prevent a loss of the aircraft, and let's look at maybe the mission loss. Well, the mission loss would be performing flight testing. If we're doing things that are preventing us from accomplishing that testing, that's a mission loss. Step two, create the control structure. I will give you the control structure in the interest of time here. We've got the physical UAV on the bottom. We've got the UAV automation, the fancy computer there in the middle. What can that do in terms of commands and decisions? What can land itself? And it can decide to wave off. It detects slide slip at altitude with its onboard sensors, and it uses that, of course, to estimate what it thinks the surface wind is going to be. Now, what does the flight tester do? Well, the flight tester can request and initiate the landing, and the flight tester can override the automation and force a landing. And the flight tester does receive a notification of impending autonomous actions, not just a landing and a wave off, but basically if it's going to do something, you generally want to let the flight testers know in advance, and they have a screen that they can watch with this info. They also, of course, get clearance to land and surface wind conditions from the tower. So here's a very, very simple control structure. Let's see if we can get something useful out of this. Step three, identify unsafe control actions. So here's a table. I've filled out the areas that are generated for you. We've just got to fill in the blanks. In fact, we're only going to do one of these. Let's give me a second to pull it up. Let's do the very first one. The flight tester does not provide force landing command when what? So you could think in terms of mission loss, not getting testing done that we need to, but is there a context in which you really, really need to force a landing, or you're in more trouble than losing flight data? Fantastic. Lots of you are proposing, what if you're out of fuel? Absolutely. That's a fantastic one. That's the one I was looking for. There are others, of course. I was looking for that one because I've got some slides prepared for it. But of course, you would do all of the UCAs if you had time for a full analysis. Let's go to the last step of STPA. Let's just build maybe one scenario here. So what we're going to do is start with the unsafe control action. This is just a real quick sketch of a slide here to have some kind of visual for you. Let's take that UCA here. Let's say the flight tester does not provide a forced landing command, which is overriding the wave off, when fuel is low and there's nothing wrong. We can land just fine. We know that because we have direct surface wind information and the fuel is low, so we really better land. If you don't force a landing, we could lose the aircraft and maybe worse than that, depending on where it crashes. So what kinds of beliefs, and I'm going to open up the next poll. What kinds of beliefs would explain why a flight tester might not force a landing in this situation? What might they believe that doesn't match reality? You want to, in your mind, you want to think about this with the words flight tester believes. That's not a rule, but it's a great way to get you to the answer quickly for beginners. Yeah, if they believe that the fuel is not low, they think they've got plenty of fuel, of course they're not going to intervene. What if they believe that the surface winds are excessive? Then maybe they're not going to intervene then either. What else that's not written on this slide? Yeah, there are lots of answers here. I only have time to pick out a few of them. One of my favorites is they believe it's not going to wave off. Why would they override it if somehow they don't think it's going to abort the landing? That's a fantastic belief. Let's take that one and run with it. What kind of input to the flight tester might cause them to believe that it's not going to wave off? So some of the things to consider, and I'll flip back to the control structure in a second. I'm gonna open a different question now to answer this one. Some of the things to consider when we're looking at feedback. What if the feedback is missing from the design? You might postulate and examine that case. What if feedback is not sent? It's in the design, but it's not sent for some reason. What if the feedback is sent, but it's incorrect? And what if it's delayed? Now let me go back to the control structure so you can see what feedback is there. And someone put the two together. It's very easy. It's not meant to be hard, but someone put the two together in a sentence for me. What's the indication or lack thereof that can cause this? You forgot it. Fantastic. I mean, there's lots of answers there and not just one. But right at the top is going to be, what if there's no notification of an impending wave off? We have just this blanket statement that we all know we should just let them know if we're going to do something autonomously. But what if somehow that got missed and there's no indication in the design, or maybe it's in the design, but it was never sent? We are done with this exercise. The reason I propose this is because this actually happened. I'm going to paraphrase a bit. But essentially what happened, and this was during testing, so this is not a bad story, I guess, for lack of better words. This is a success story because this is the purpose of flight testing, to find things that the designers missed in part. And one of the things that they discovered is they had lots of different indications to the flight testers of imminent actions, but nobody provided to the flight testers that this thing is about to wave off due to crosswind. There are maybe 6 or 9 other conditions that it would tell the flight testers I'm about to wave off due to X, Y, Z, but no one put into the display that this is going to wave off due to crosswinds. The other thing, and related to that, is they didn't put any feedback about what the altitude winds that were detected actually were. what was it assuming the surface winds were? It was never displayed for the flight testers. So even if they knew that that was one of the hooks that triggers wave off, they had no way of anticipating that it would happen. Now, on an engineer's console somewhere else, they had access to that data, but nobody thought it would be useful for the flight testers to have until they actually started flight testing and it was coming in for landing, and the thing waved off and the flight testers are sitting there, what's going on? Why is it doing that? It told me all the other times it was going to wave off, but not this time. And it happened a number of times, and they realized, all right, we've really got to bring this on the ground and force a landing, without really understanding what's going on, with being blind to the reason why this thing kept waving off. And if only we had some method that we could use to maybe anticipate these things a little bit earlier. I think flight testers would love that. Engineers would love that. That would kind of be a win-win.